Here's an example of something which is not a vector space. This is a set W. It is a subset of R2, of 2 space, so it lives somewhere in 2 space. Let me just draw it here so we have a sense for what it's supposed to be. So this is R2. The set W looks like this. I'm going to make you notice something important. It does not go through the origin, right? Graphically. That's usually enough to show that something is not a space, a vector space. It's just a set. There's a difference between a set and a vector space, right? Vector space has to satisfy the conditions. But anyway, a drawing is not typically sufficient. We need a little bit more than this. If you're trying to show that something is not a vector space, you don't need a proof. All you need is one example of one axiom that fails once. So it's much easier in general to show that something is not a vector space than it is to show that it is a vector space. The defining property of W, the membership condition, is that a point is in W if its second coordinate not twice as much, but 2 more than the first coordinate, right? That's what we have here. So for instance, the point 1, 3 is in W because the second coordinate is the first one plus 2. But the point 0, 3 is not in W because the second coordinate is not twice more than the first one. Or not twice more, sorry, 2 more than the first coordinate. So here's an example of the closure not being satisfied. I pick 0, 2, which is in W. I pick 1, 3, also in W. I add them up as you normally would. 0 plus 1 is 1, 2 plus 3 is 5. Great, but 1, 5 is not in W because the second coordinate is not 2 more than the first. Or you can do the stretching. 0, 2 is in W because the second coordinate is 2 more than the first. But if I multiply by 2, I get 0, 4, and 0, 4 is not in W because the second coordinate is not 2 more than the first one. 0 itself as a vector is not in W. I pointed it out when I did the drawing because the second coordinate is not 2 more than the first one. And so on and so on and so on. Now the algebraic properties would all have been fine because the operations are fine. It's not the operation that's the problem here. It's not the vector sum or the scalar multiplication that's the problem. The problem is that the subset of R squared that we picked was bad. I'm going to go back on something here. I'd mentioned that, it's not surprising that V here was a subspace because it's basically a copy of R that has been rotated, and R is a subspace. But you could argue that, W is also a copy of R that has been rotated. It's just been rotated around another point. Like here, what you really want to say is that V is a copy of R that has been rotated through the origin. Like W is a copy of R that's been rotated through that point here. And that point is just not the right point to rotate against or rotate around. There's something there to keep in mind. A matrix is a table of numbers. Now this is going to give us an example of a first example of things that are not vectors, at least not arrows. Now you've encountered matrices presumably before. I'm going to ask you to sort of forget what you know about matrices, and now you think of them as arrays. They have rows, they have columns. So this here is a 2 by 3 matrix. Typically, if we say that a matrix has size or dimensions m by n, we mean that the first one is the number of rows, and the second one is the number of columns. We really should be saying the size is m by n, not the dimensions. Dimension, we're borrowing from regular speech, regular English dimensions, you know, the size of both things. But dimension means something else in linear algebra. So as much as possible, we'll try to avoid talking about the dimensions of a matrix. I should talk about the size of it from the context, though when we slip, it should be clear that we're talking about the number of rows, number of columns, even if we say dimensions, because then it won't make sense with the other formal definition of dimensions. But still, be on the lookout for that. You can add two matrices together as long as they are of the same sizes. And you can multiply a matrix by a scalar as well fairly easily. How does it work? You add them, roughly speaking, in the same way that you would add n-tuples or arrows, component by component, or as we say in mathematics, component-wise. So if I'm adding the 2 by 2 matrix 1, 2, 3, 4 to the 2 by 2 matrix 5, 6, 7, 8, I start by adding together the first components in the first row, then the second components in the first row, then the the first component in the second row, and the second component in the second row. Did a bit of a slip there. It wasn't planned, but I started saying the third component. Look, the reality is that you can decide to view a matrix 1, 2, 3, 4 as really like a vector 1, 2, 3, 4, which you've just decided to wrap around after the second entry. And in fact, you can argue that an m by n matrix is really a vector in m times n space. But it's convenient to place them in array form, and we will treat them differently. For those of you who are interested, you can also think of this as like, well, why do we restrict ourselves to two-dimensional arrays? Why not have like a three-dimensional array where we put the numbers in sort of a cube instead of a rectangle or a prism? And not why stop at 3, why not 4, 5, 6, and so on? You can do that. If you do that, you're working with tensors instead of matrices. Tensors are some of the basic objects in physics, obviously, when you look at general relativity, but they're also basic objects when it comes to deep learning, especially when you're trying to do image processing, image recognition in deep learning networks. At any rate, you can add matrices together. You can see why the sizes have to be the same. If the sizes weren't the same, if at some point there was another row here of numbers, what do they get added to? There isn't something here to add them with. So the dimensions have to be the same. And scalar multiplication basically works on you applying the scalar to each of the entries in the array. All right, so this is what you would expect it to be. That's the only sort of natural way to define a sum of matrices and a scalar multiple of a matrix. Now, if you look at the set, which consists of all of these arrays, it has a special name. Here, we're looking at the set of 2 by 2 arrays, 2 by 2 matrices, right? This is m for the number of rows, and this is n for the number of columns. That set is also a vector space. Well, here we're going to do it for the 2 by 2 matrices, but you could show that this is true in general for m by n matrices. A space or a set alone cannot be said to be a vector space. You need to tell us what the operations are. In mathematics, we say that a set is endowed with operations. You need to know what the plus is and what the scalar multiplication is. But we've defined those previously. Okay, so again, I'm reminding you, if you want to prove that something is true, you cannot give examples. You have to check the axioms. mean, you can use examples to convince yourself that it's true. Sometimes the question won't be prove that something is true. Sometimes the question will be, is this true? Here, we are telling you that this is supposed to be true. How do we go about proving it? Well, you have to show the closure axioms, you have to show the existence axioms, and you have to show the arithmetic properties. I say here that it is clearly closed under addition and scalar multiplication, because if you add 2 by 2 matrices together, or if you multiply a 2 by 2 matrix by a scalar, the result is itself a 2 by 2 matrix, right? And this is what we did here. I mean, I've given you an example of how these things are built, but the definition is obvious. You just add things component-wise, or you multiply them component-wise by the scalar. So that is going to be obvious, the closure. Great, okay. In this case, we're safe. We also have to find a zero vector, something that plays a special role that when you add it to anything else, it doesn't change the anything else. And we have to show that there's a negative. Well, the zero vector hit, the only thing it could reasonably be is the 0, 0, 0, 0 matrix. And sure enough, that is a 2 by 2 matrix, and it satisfies the property that when you add it to any other matrix A, whatever A is, the result is exactly A, because component-wise, you'd be adding 0 to A, that gives you A, 0 to B, gives you B, 0 to C, gives you C, and 0 to D, gives you D. It has to be that way. Great. There's also the existence of a negative, and again, the only thing that makes sense, if A is your vector, 2 by 2 matrix, A, B, C, D, then the negative of A would have to be the matrix that contains the negative of all of the components. And that is such that when you add them together, A plus minus A, B plus minus B, C plus minus C, and D plus minus D, you get 0, so that A plus minus A is indeed the 0 vector. Now the 0 vector here has a special little notation. I write it 0, 2 by 2 to remind us that we are living in the space of 2 by 2 matrices. If we were instead working with like 6 by 9 matrices, then this would be 0 of 6 times 9, reminding us that there's a 0 in all of these locations, and there's 6 rows and 9 columns. In this case, 2 rows and 2 columns. The other properties are easy to check. You check them as you would in R4, right? Because the 2 by 2 array is basically an R4 vector that's been wrapped around. It's pretty straightforward. I'm going to show you one of them to see how you would go about proving this, but you should do the other ones as exercises. Eventually, you develop an intuition for these things. It's like, well, obviously this is going to be like R4. I don't need to redo it, but it helps to have a bit of mileage under your legs, so to speak, that you've tried it for a few of them. So let's look at number 7. Number 7 says that if you have 2 vectors, u and v, and you add them together and you multiply by a scalar, c, so c times u plus v, that would be the same thing as c times u plus c times v. All right, so what does a general u look like? As a vector, it is a matrix that has 2 rows, 2 columns. So it'd be like u1, u2, u3, u4. V, on the other hand, is some other vector, another 2 by 2 matrix, v1, v2, v3, v4. In practice, it's conceivable that u1 is equal to v1, potentially. But in general, no, we don't know. And then we pick a c in the set of real numbers, a scalar, a general scalar. Then if you do c times u plus v, what is that? Well, first you add the vectors together. So the vectors are matrices. When you add them together, you add them component-wise. So you add the first components, the second components, the third components, and the fourth components together. Great. Then you do the scalar multiplication, which is that you take c and you multiply it by each of the 4 components. And so you get C times U1 plus V1, C times U2 plus V2, C times U3 plus V3, and C times U4 plus V4. That is the scalar multiplication of C with the vector U plus V. Once you've done that, you simplify a little bit, you rewrite the terms. CU1 plus V1, that's the same thing as CU1 plus CV1, because U1 is a real number, V1 is a real number, C is a real number, and multiplication of real numbers is distributed by the sum of real numbers here, right? So the plus that shows up here is a plus for real numbers, the plus that shows up here is a plus for matrices. It looks the same, we use the same notation, we mean different things. By the properties of real numbers, this is CU1 plus CV1, and similarly for the other four components. And now you can sort of split them up because there's two terms to each sum in each of these vectors. Again, here I'm back to matrix sum, not real number sum. Like I had here, just separate them, and then I can sort of take away the C. There's a C that's common to everything here, and I end up with C times U plus C times V. So the seventh axiom holds. You would do this for the other five arithmetic properties. It gets a little boring after a while, right? Because you figured out the trick. But until you figured out the trick, you got to slug through it until, you know, it becomes intuitive. Can't help it. That's not only going to be the case for 2 by 2 matrices, it's also the case for any m by n matrix. If you have analogous operations, it's a vector space. There's another example, and this example usually creates a little bit more confusion. I took some pain when I did the examples about the matrices to call the matrices vectors, even though they were clearly matrices. So remind you that, yeah, it's a matrix, but it behaves as a vector would, because we're trying to show that the thing is a vector space. It's never a bad idea to sort of force that choice of terminology, especially here when you're talking about function spaces. We'll define the closed bounded interval AB as basically anything on the real line that is found between A and B, including A and B. So I mean, from a graphical perspective, AB might look like all the points here, including the endpoints. Okay, here's a new set. It's a special set, fancy F and the closed interval AB. How is that defined? Something is in that big set F, little f, if little f is a function of AB to R. So perhaps something like this. That is a function, at least it's the graph of a function, the representation of a function. So the big set here is all the functions from AB to R are in here. This is another one. Here's one that is not in there. Suppose it's an asymptote here. That point, that function, not in AB because it is not defined at that point right here. Okay, so you look at all the functions on AB that have values in R. That's the set. There's infinitely many things in there, but it's a set of functions. So x squared is in there if I use 0, 1 as my AB. 1 over x minus 2 is in there, but the function that goes from 0, 1 to c that gives you e to the ix, and I remember e to the ix in the complex world, that's the same thing as cosine x plus I sine x. That is not in this space F01 because some of the outputs are complex numbers that are not real numbers. And the logarithm of x is also not in the function space over 0, 1 because it is not defined at 0. These functions are actually vectors. They behave as vectors do. If you get two functions together, you can add them and get a new function. If you have a function and a scalar, you can multiply the function by the scalar and get a new function. But before we get too carried away with this, we have to recognize or remember that this is only going to be useful if we have a way to tell when functions are the same and when functions are different, right? We had a way to verify when three vectors were together the same. If the first components are the same, the second components are the same, and the third components are the same, then these vectors are the same. Well, what is it like for functions? How are functions the same? Functions are the same if they have the same graphs, which means that if they take on the same value for the same inputs, for all possible inputs. If that's the case, then that set of functions is a vector space. Things act as vectors. Right? How do we add things? Add by adding, you add functions, you add vectors by adding the output that the function takes at every specific x. So this new function h, which is the sum of f plus g, notice here I'm not writing the x. Just h as a function, it's the sum of f plus g. Well, it's the function that is given by the following definition. H at x, if I want to see the output of the new function h at any given x, I simply add the output of the function f at x to the output of the function g at x. Scalar multiplication works the same way. If c is a scalar and k is a vector, sorry, let me rephrase that. If c is a scalar and f is a vector, then the function k, which is c times f, is a new function, and that function is defined by the following rule. The output at k, at x of k, sorry, is c times the output of f at x. From a geometrical perspective, what this means is that when you add two functions together, f and g, you add their graphs vertically. And scalar multiplication is a scaling of the graph, f by c. This is a vector space. The only thing that's really missing is the existence of a zero function. Now, a zero function is really a zero vector, right? We need to have something that plays the role of zero. Now, what is a zero vector in the function space? It's got to be some sort of a function from AB to R. That's what it means to be in that function space. We're going to call it here fancy O so we can differentiate it. It's the function that no matter what input you give me, the answer is 0 as a scalar number. So if you were to draw this, let's say this is AB. The 0 function is the function that is basically that horizontal line right here. So that is a function in this function space. And it behaves as you would expect it to behave with respect to addition and scaling. The negative of a function then would be the reflection of the function here in the x-axis. And then the sum of these two functions gives you back the 0 function, right? All of these points annihilate one another. Set of functions over a closed bounded interval is a vector space. The vectors are functions. The sum and scalar multiplication of vectors is the sum and scalar multiplication of functions. and there is a zero function that plays the role of the zero vector. Now, if you were to look at a different set, here f on R, we don't restrict ourselves to the closed bounded interval AB. All the functions from R to R, it's also a vector space if I use the same function addition and multiplication of a function by a scalar as I defined before. Sine of x would be an example of a function here. Now, technically speaking, I shouldn't call this sine of x. I should really call this sine. Sine is the function in question, and sine is a function where to any input x, I output sine of x. So sine of x is the output, sine is the function. But we'll abuse the notation here and say that sine of x is in that space. Same thing for every polynomial you can think of. Every polynomial in x is a function in that bigger set, the set of all functions. But 1 over x isn't. Neither is the tangent of x, because they're not defined on all of R, and e to the ix isn't, because it's not a function from R to R, it's a function from R to C, and some of the outputs are not in R. In most of the examples that we've done, although it's not guaranteed to be the case, but in most of the examples that we've done, we didn't really need to worry about axioms 5 and 10, right? Because we had proven that whatever the sum and the scalar multiplication were in a bigger set, what we call a superset of vectors, it applies. So it also has to apply to the smaller subset. There is a shortcut for you to check if something is a subspace when you're looking at a subset of something that you already know is a vector space, assuming that the subset is endowed with the same operations as the space itself. You heard me say as well, before we move on to that shortcut, you heard me say that I've called the negative the reciprocal or the inverse. Choice of the name doesn't really matter that much. Negative makes sense because we're reminded of the fact that there's an addition, but inverse also makes sense if you abstract away the meaning that inverse typically means a multiplicative inverse. And when we talk about group theory, we call all of these things inverses. If there's an operation that basically gets you back to the special zero vector or the special null element. So you can call them inverse, reciprocals, negatives. It should be clear from the context, especially since in linear algebra we don't really have inverses, except when we start talking about matrix inverses, which are clearly multiplicative inverses. But we'll point that out when we get there.